So in this video we have an integral to evaluate using a method referred to as partial fractions. Done some examples of how to break or do the partial fraction decomposition, which is taught in a college algebra course. So we can see here that the denominator factors into x minus 1 and x minus 2. So the idea then is to rewrite it. So you have the denominator factored out from the integrand, x minus 1, x minus 2. And these are linear factors. So this should break down into something that looks like this. Some number, some constant over x minus 1 plus another constant, b, over x minus 2. If you had three linear factors, then you'd have another term over here, c over that factor, and so on. So this is a case where you have distinct linear factors. Then there's another case where you could have repeated linear factors or irreducible quadratics. This is the easy form of the decomposition. So all we have to do is find the values of a and b, so that when you add this up, it'll give us the original expression. So there we have it. So what we're going to do is multiply both sides by x minus 1 and x minus 2. So multiplying both sides of this equation, which is going to be an identity, by x minus 1 and x minus 2, then we're going to get x on this side by itself. And in this case, multiplying by x minus 1, x minus 2, the x minus 1 will cancel here. So that'll give me a times x minus 2. And then on the second rational expression, the x minus 2 cancels, and you get b times x minus 1. Now in this case, we can just go ahead and do a substitution. Since this is a identity, we can just plug in numbers, any number you want. But let's be smart about this. If I replace the x by 2, it wipes out this factor. So replace the x by 2, x equal to 2. What does that give me on the left side? Well, I only have an x there, so that should be a 2. On the right side, putting a 2 where the x is, this gets wiped out. That goes to 0. Putting a 2 there where this is, 2 minus 1 is 1. That gives me a b. So b equals to 2. That's the value for that one. Now we need a. Again, we can get a the same way. Replace the x by 1. So what happens if x is equal to 1? Put a 1 over here on the left side, we get 1. On the right side, put a 1 there. 1 minus 1 is 0. That wipes out the b, and I'm left with a. And then a 1 minus 2 here, that gives me negative 1. This will be negative a. Solve for a by multiplying both sides by negative 1. We get a is equal to negative 1. That's how easy that is to find the constants. A is equal to negative 1. And b is equal to 2. Now sometimes it gets a little bit more complicated, so that's the easy way to do it. When you have more involved expressions, we can do something like this in combination with the steps that I just went through. So in this case, what I would do is that x equal to, and then I would multiply here. A times x is ax, b times x is bx, and then we put those together. A plus b, x. And then what's left? We have a minus, so I'll put a plus here. And then a times a minus 2 is a minus 2a. And b times a negative 1 is a minus b. So when you get more complicated expressions, you can set something up like this. You might have, over here on the left side, we have a linear expression. In some cases, it could be a quadratic. So the coefficient of the x here should be the same as it is over here, because this is an identity. So the coefficient here is a 1. So a plus b should also equal to 1, because that's the coefficient of the first degree term on the right has to equal to the coefficient of the first degree term on the left. Okay, now this is constant, there's no x, and minus 2a then minus b has to equal to the constant, the same constant that's on the left side. Well, on the left side there's no constant, so that's 0. So we just set this equal to 0. And then we just solve this like a system. Plus b equal to 1. And then we solve this system. We can solve it by elimination. Minus b and b go to 0. Minus 2a and a is minus a. And then 0 and 1 is 1. So minus a should equal to 1. Multiplied by negative 1, a should equal to negative 1. And then we just take either one of these, it doesn't matter. I'll take the second one, put a negative 1 there for the a, and solve for b. Negative 1, add a 1 to both sides will give me a 2 over here. 1 and 1, so b equal to 2. Those are the constants. And when you have a more complex integrand, it gets a little bit more involved, but the steps are pretty much the same. So now that we have the constants in, we can go back over here then and just write it out this way. This then should equal 2. The integral, we break this up then into the partial fractions using the integral sign here. We'll have then a over x minus 1, and a was negative 1. So this gives me negative 1 over x minus 1. And then it was a plus b over x minus 2. And we found b to be 2. So we have 2 over x minus 2. So instead of integrating the original integrand, this right here is broken up into minus 1 over x minus 1 plus 2 over x minus 2, and then we can just integrate. Very basic here. Don't have to, you could use the u substitution, but all you're going to have, if you use the u substitution, it'll be the integral of minus 1 over u du. Over here, it'll be 2 over u du, replacing the x minus 1, let that equal to u, x minus equal to u. Again, it's simply going to be the natural log of negative 1 can come over here as a coefficient. I'm just taking the integral over this first, and this is the absolute value of x minus 1. And then for this one, it's going to be, let u equal to that, the integral will be 2 over u, and then that has an answer of 2 natural log of absolute u, which is x minus 2. So this I'll write this as a plus 2, and this will be the natural log of absolute x minus 2. And you have your constant of integration. So again, using partial fraction decomposition, the original integral breaks down this way, and then we just take the integral individually of each of these. We get minus 1 natural log of absolute x minus 1 plus 2 natural log of absolute x minus 2 plus a constant. Thanks for watching. We'll see you next time.